discussing a recent presentation by Sergey Levine at U Toronto, Foundation Models Robotics. He goes through sort of analytically how his new company, Physical Intelligence, and his general work, his work at university, is sort of moving towards a foundation model for robotics. And I think it's really interesting the way he phrases it. He calls it the anatomy of foundation models, and they borrow from the language models that use a pre-trained data set, which is diverse and not very high quality, usually trained through self-supervised learning. So there's not a lot of expert knowledge, not a lot of curation, fine-tuning, none of that. It's just raw, unsupervised learning through the transformer architecture. And then you have the fine-tuning, which happens either just through prompts or a little bit more sophisticated through RA, reinforcement learning, human feedback, or most recently with reinforcement learning and test time scaling. So where you start using compute at inference to actually enhance the model without changing the weight of the model. So those developments that have led to really interesting developments in the language model space, they are also translating into robotics, and that's what physical intelligence is doing. That's what, in my opinion, robotics should be doing, and it's very interesting also for us here at Orange Capital Partners. We're invested in robotics very heavily through our positions in Tesla and NVIDIA. I also want to mention Vladlen Koltun's work on this is a presentation about a year ago at MIT, but it's about reinforcement learning. He calls it a silent revolution in robotics, and it's the simulation that is really gaining traction in robotics. Now, Sergey doesn't particularly talk about that, but I want to combine those two because I think the foundation model for robotics in combo with simulation and reinforcement learning applied to simulation is really going to propel robotics to a level where we're going to see commercial applications coming out pretty fast. This is not even on podcast. It's May 16th, 2025. This is Cream Delco. For the year, we're down 12.5%. The market's up 1.5%. Excuse me, we're underperformed by 14%. We had a pretty good run recently. We were still down 12%, but obviously we were down a lot more. So this is really good for us. We have recovered quite some ground, and we've also had some conversations about if that's warranted and what's going on, how should we position ourselves, all of these things. Now, the purpose of this podcast series is to give people a sense for what it feels like to run a hedge fund. So it's important to talk about positioning, to talk about sizing, to talk about trading. We like to talk about research and foundation models, and that's part of this episode. But we don't want to neglect the day-to-day business. And if you want to understand what it feels like to run a hedge fund, so this is a good example. So we had a drawdown in the worst times of maybe about 45%. Now we're down to 12%. So we recovered about 30% of our portfolio, which is a lot of money. And you have to ask yourself a few questions. Why was the drawdown so drastic? Why was the recovery so drastic? And of course, the big question, where is this going? Actually, to paraphrase something that Sergey Levine said in this presentation, that some tasks require different levels of abstractions. So surfing requires a raw data input, and feeling and, let's say, doing math or writing an essay requires a different level of abstraction. So the same way, when we analyze our portfolio, we might use, the level of abstraction is like, you don't want to look at daily, stock moves. You don't want to look at, even monthly or quarterly portfolio moves. I mean, you have to, of course, I always say that, look at them from a sort of leverage perspective and manage your cost. But from a return perspective, those things might not matter that much. What you really want to care for is the level of abstraction is, for example, like what is the technology and the wave of technology, and how can we expect this to turn into commercial success and revenue and earnings, which ultimately drives wealth creation. So that level of abstraction is very different than looking at daily stock prices. So I think that's obviously what we choose. We try to keep it relatively high level. So we don't think that here at Orange Capital Partners, and this is really us and our fund, and that might vary for other funds, but for us, the key is not to look at daily moves of trading. We don't look at daily news. We don't follow commentators. We don't follow technical charts. We really follow at the big picture. And the big picture is this presentation by Sergey Levine, I think, is a good example of what the big picture is. So we are here at the crossroads of a new evolution in AI, which is embodied AI. And the anatomy of foundation model for robotics, which is what this presentation is about, explains how that works. So there's a real technique to it. So we start with, and now I'm just paraphrasing a little bit what Sergey, but check the actual presentation, the show notes. So it started with something called RTX, which is, let me go even further back. So robotics, like other AI tasks in the past, has been sort of harassed by the tyranny of siloed data. What does that mean? So if you wanted to develop a robot that can, slice bread, you had to train the robot to slice bread. If you want to train a robot to fix a tire, you have to train the robot to fix tires. So every task has to be trained, explicitly, and that's very, very difficult. It's difficult to create something useful like that, because that's what robots are right now. They're very dedicated tasks, one specific thing. The KUKA and the Fanuc robots of this world, they're very specific. They do one thing. They screw a screw, or they unscrew a screw, or they do stuff like that. They bottle water, Coca-Cola, things like that. Those are what robots actually do. What we want is a general robot. Maybe humanoid robot, maybe not. That doesn't really matter. The embodiment, it's a different question, the embodiment. But what we want is a generalized AI embodied in something that can do all kinds of things. So we can put that thing in a factory, and maybe even without any instruction, other than maybe a high-level instruction which says, just clean the place so it's safe for humans. And then, the robot just walks around and makes sure everything is clean, and constantly dusts stuff. Maybe in a semiconductor factory, this could be useful, where we have constant cleaning, and we don't have to train the robot specifically how to clean certain types of dusts from certain types of surfaces. It has this general knowledge of how to do it, very similar to humans. Like if we drop a human in the Amazon jungle, chances are they will survive because they have this general knowledge. And I think it was Sergey who years ago said his dream is to build a Robinson Crusoe robot. You drop the thing on an island, and the thing just figures out how to survive. In the case of a robot, let's say, build an energy source, create a shelter for its batteries so they don't overheat, stay away from water, like things, like it just figures stuff out. So anyway, so how do we get there, right? That's the idea of foundation models. And the history of foundation models, as Sergey Levine tells it, is for robots. It starts with RTX, which is a project within Google that collects different types of data. So it tries to overcome the tyranny of data silos, different types of data from different labs, and trains all kinds of specialized tasks in a general model, and then realizes that the generalist is better than the specialist in the specialized task. So this is RTX. Then RT2 does the same thing, but also with different embodiments. So equipped with that kind of knowledge, Sergey and others form Physical Intelligence, which is a company now that is trying to build foundation models at a larger scale. I don't know what their commercial strategy is, and this is not the topic of this podcast. But it's a company, it's a startup full of high-level academics from Berkeley, Stanford, and others. And they start with vision language models. So vision language models are models that see things and then turn it into language. So I see a banana and I know what a banana is. So I don't have to teach the robot what a banana is. The vision language model uses the large language model knowledge, the semantic knowledge of what a banana is. So the robot has a sense for what a banana is. Now, and it has a sense for what a tree is and a chair and all these things. So vision language models are good in understanding, okay, what's around, what do I see? But not just what do I see in terms of point cloud, like let's say the Tesla car right now. I believe my FSD doesn't really know what it sees. It just sees things and it understands that it can't, it shouldn't be hitting those things. Although it does have a bit of a semantic understanding of what a pedestrian is and what a tree is. So it has a bit of that. But imagine if you put a vision language model on top of the FSD, it would really have a very good semantic understanding of the world, and it would understand that the tree is not a pedestrian, and that maybe an animal which is turned around from you is not going to jump on the street, but an animal which is facing you might jump on the street. So it might have those types of semantic understandings. So that's vision language. Now, what Sergey and his colleagues are doing now is creating a vision language action model. So this would be the equivalent of what Tesla has with FSD, right? FSD is a vision language action model. Actually, it's a vision action model, not a vision language action model, where you see things and you connect it straight to the actuators. So you have actual actuator data connected to vision. And the VLA is the language in between, just sort of translates the vision from, okay, I see a banana and I'm gonna pick up the banana. And then the pickup is the action. So that's the first phase of this presentation. So what's really interesting is the second phase, which is the reasoning. So like in the language space, we have reasoning, which is the idea that we have chain of thought, which has been the big thing in 2023. Chain of thought is so we can by clever prompting, get more out of a model. So we don't have to pre-train. We don't have to pre-train. We have a pre-trained model. We don't have to change the weights of the model. We don't have to actually impact the knowledge which is compressed in the pre-trained model. What we do with chain of thought is we find clever ways to reason around certain tasks and figure it out. And we can do the same thing with robots. So reasoning is, according to Sergey, a very big sort of innovation. And then finally we come to RL. RL is now, what is RL? Reinforcement learning is where we have the robot actually doing, trying to actually, complete a task after it's been pre-trained. So we have now the pre-training, which gives it a very robust, diverse set of data with lots of knowledge, but it's not particularly good at now doing a task. So we can now use reinforcement learning and distill it onto the VLA. So what that means is we can use the reinforcement learning that the model has been trained on, let's say, unscrewing a screw or making a sandwich, and that particular expert, the reinforcement learning expert, now gets distilled onto the VLA. So the VLA is sort of being trained in a supervised method with the reinforcement learning being the ground truth. And that leads to much better performance. So that's kind of what, so we have pre-training, and then we have fine-tuning with RL, sequential reasoning, test time compute. So we have all these concepts that have worked in the large language model space, and they're being applied to the robotic space. And I think this is sort of what the presentation actually, what the presentation means. And I think this is really profound, because what we're talking about here is a blueprint for a generalized robot that can do things, and also a way to train these robots and scale these robots up. That's really what this is. And for us here at unsupervised Partners, this is very important, because we believe that there is a huge opportunity, a commercial opportunity for generalized robots that can be deployed in areas where humans shouldn't be, like danger areas, clean up after waste, nuclear waste or fire hazards and things like that. And then later maybe even used in areas where humans don't want to be, or we don't have enough humans, such as elderly care, for example, things along those lines. There's a lot of open questions. So the Q&A, for example, what do you do with the degrees of freedom? So when we have how many degrees of freedom do we train the robots with, and what if we have more or less? How do we adapt that? So that's an open question. Data requirements. Sergey said in the pre-training you want quantity and diversity, and post-training you want quality. You can have reinforcement learning also with priors or prior data or human intervention. So you can have humans actually impacting the reinforcement learning process, so making it faster. So this is a little bit similar to what Tesla's doing with shadow mode and driving, so the human actually fixing it. The question, do we need more world models or just end-to-end training? And I think that's what I just mentioned a little bit before here. Sergey said that certain things, certain tasks require different types of abstractions, and therefore it's not clear. Sometimes you need a world model, sometimes you don't. It's not an if or. I think if you want to build a lithium-ion battery, you need some sort of world model to have even a clue of what to do and where to do research. But if you dance ballet or dancing in general, I think is pretty good to just raw data and action. So from raw data to action, driving is one of those skills. So maybe the kinds of stuff, the things that we learn and then never forget, like driving, riding a bicycle, skiing. Those are the kinds of things where we don't need complex abstraction. We can just do raw data in and then action out. But then if we have more sophisticated skills, for example, what is good driving? Let's say driving, if you drive a president, or if you drive a elderly person, or how do you drive so people don't get sick? When it gets a little bit more abstract, we need more empathy maybe. You need to understand who your customers are. You need to understand the environment. Maybe you don't want to also disturb the environment. When it comes to those types of things, maybe raw input is not enough, and abstractions could be helpful. So in my opinion, this is actually something new that I haven't really thought about this too much. I was sort of a bitter lesson type person, but it looks like there is also a case to be made for priors and some expert knowledge and things along those lines. And then, of course, the canonical question in every AI is, what kind of data do we need? And again, Sergey kind of gave a pretty good answer here. In the pre-training, we want very diverse data, some quality, but also low quality data. In other words, we want to have data where people fail, like let's say in the FSD example, people that don't drive that well, because we want to learn from bad driving too. And then in the fine-tuning side, we want expert data, and reinforcement learning maybe enhanced with expert data, so we can really execute the task. But we need mistakes. We need to learn from mistakes. The same way humans need to learn from mistakes, I think robots should also be learning from mistakes. So to summarize, foundation models for robotics, very, very interesting. As always, Sergey Levine, in my opinion, is at the forefront of this with others. He's not the only one, but he's definitely one of those that you want to listen to and care for. We're going to ICRA next week, so there's going to be hopefully lots of interesting new insights from robotics. For us here at Orange Capital Partners, we are interested in robotics because of all these events. And again, I want to just mention also simulation. Let's not forget simulation, which can be, I would say, if you use this framework, simulation is, in my opinion, sort of it's much more than just a cherry on the pie. It is really the thing that makes reinforcement learning actually work and gives reinforcement learning the power that it deserves, because otherwise reinforcement learning is a very cumbersome process. But if you can have proper simulation, and Vladlen Koltun in his presentation about the drone race, links in the show notes, he really opens up my eyes to the opportunity, what's possible with reinforcement learning. Simulation and reinforcement learning really are the same thing, in my opinion, because without simulation, reinforcement learning is a nice to have, but with simulation, it becomes a really, really powerful tool, and you can drive superhuman intelligence for embodied agents with simulation. So to summarize, I think Sergey's presentation is giving the blueprint for the anatomy of foundation models. Vladlen's presentation gives you the blueprint for simulation. Together, I think this is where robotics is going, and we believe that this is dramatic in terms of the impact it's going to have on robotics, and arguably also on the rest of the world, because robotics as an embodied intelligence will have a lot of impact also on commerce and people and social aspects and all kinds of things along those lines. Thank you.